In this presentation, we will show how to build VR and AR experiences with CityEngine, Unity, and Unreal Engine 4. My name is Stefan Arizona, and I will guide you through the slides. Briefly about the agenda, we will introduce two game engines. Rather generally, game engines are basically the fundament for building VR experiences. I will then give some CityEngine user examples. A question that always comes up, should I use Unity or should I use Unreal Engine? Then I will make some remarks about importing GIS data in general. I will show in practice how this works to import GIS data into Unity, the same thing to work with Unreal Engine, and I will give a summary and an outlook at the end. So, introduction to game engines. What is a game engine? A game engine is a software development environment designed for people to build video games. At the core is typically a rendering engine for 2D or 3D graphics. It supports multiple devices such as desktop computers, mobile devices, consoles, and also VR and AR devices. It contains subsystems for animation, game AI, physics, audio, also cinematics, virtual production. Asset management is a very important thing since game engines basically live from having assets available that can be used as content. Increasingly, they also include editing tools, so you can, for instance, editing your meshes. They are typically extensible and scriptable, and there's a number of additional subsystems such as for networking, memory management, debugging as well, threading, localization support, and so on and so on. But let's just have a look at what game engines actually can do in the following video. So that was a recent Unreal Engine demo reel. Very exciting stuff. So why should we use game engines to build AR and VR experiences? Typically, VR and AR experiences are use case specific applications. They are strongly focused on story. The functionality is intentionally limited. They have a real-time UI and UX. They are very much centered on content and graphics intense, and they need to support a variety of VR and AR devices. These characteristics make them a good match for game engines. In this video, you see a recording of the CityEngine VR experience. The VR experience is developed here in Zurich at our lab. So you see, you find yourself at the virtual planning table where you can navigate around. On the table, you find a city. You can rotate this city. You can have a look. You can pan around. There's a number of different options. For instance, you can look at different scenarios, so you can see at what is built right now, what you might want to build in the future. You can change the daylight. You can also directly interact with the table by moving the controller there and interact with the handles. In the CityEngine VR experience, you also have the possibility to jump right into the city and then again change the scenarios to look at different options, change the daylight as before. You have a number of viewpoints which show up as teleports, so you can just jump through these portals. This gave you a brief overview of the CityEngine VR experience, which was just recently released with a new version. There's another characteristic of game engines where it comes to interactive experience versus offline rendering. Interactive experience such as games, touchscreen apps, and so on require a fast refresh rate, so typically 60 FPS or higher. But alternatively, game engines can also be used for offline rendering of 3D still images and video sequences. This brings us to architectural visualization, where game engines have become more and more popular in the recent years. In a recent survey by CG Architect, 25% of the users say that they use game engine technology for architectural visualization. 50% of the users say that they are experimenting with game engines, and this trend is from year to year is rising. Here we show a couple of examples of architectural visualizations we have done here in Zurich. You see a cityscape at night. You can also see that this is a time lapse, so time is moving rather fast. The morning is coming, the sun is rising, the lights will go off. This all runs at interactive rates in frame rates in real time. Now it's getting darker again. This is another shot of the same city. We have some characters on the balcony there. You can see that we also modeled some interiors. There's a lot of greenery on the balconies, which is an important point in urban planning these days. And one last shot with walking characters on the street, pedestrians. In other examples, we have also modeled moving cars, which is clearly something that can be done easily with game engines as well. So anything that is dynamic and comes alive, game engines are really well suited for this kind of requirements. The game engine manufacturers, they also have recognized that people really like to use their game engines for creating experiences. So they have been starting to create products on top of their engines. One of them is Epic's Twinmotion, which you see a screenshot on the left, which basically is a standalone application built on top of Unreal Engine, which is made for architectural visualization. Unity has a similar tool, which is called Unity Reflect, which allows you to turn Revit models into real-time 3D experiences. So next, as said, I will show some CityEngine user examples. We will start with virtual Gothenburg, where they use the CityEngine and Unreal Engine for creating a digital twin city of Gothenburg. The next example is also made with Unreal Engine by Housel and Lavinia Associates in Chicago. It's a study in Morrisville Town Center. You see here like this third-person perspective of a player walking through the city. You can also see that you have two scenario buttons and a dashboard coming up showing land use numbers. The player can now move around through the city, walk on the streets, and then switch again between multiple scenario and have a look how this would look like. So if you go higher or lower, yet another perspective here, also two different options. So this is really useful for people to experience how a city could look like when things are actually built. And the amount of realism is getting really, really high, especially by including greenery. People usually recognize the trees on the street. They use trees for orientation as well. So getting all these elements into a virtual experience is really something important in urban planning. The third example was made with Unity. It shows a scene that was made here in Zurich. It's an archaeological excavation of a 5,000-year-old pile-dwelling village. You see the big space here in Zurich, which is called Sechseleutenplatz. The village originally used to be there, and when they basically made this space renewed this space, they found all the remainings of the pile dwelling and started to excavate. So they came up with the idea, well, could we use an AR experience to show people what was originally standing there? And that's what they did. So basically you can walk around on this plaza, and through the Microsoft HoloLens, you can see the buildings overlaid with the actual physical reality. So you can see again which buildings were standing where, what elements there were, what houses there were, all the bridges and the pathways. In addition, the city of Zurich also created a virtual reality experience. So you completely dive into the original pile-dwelling village and can have a look at how this might have looked like at the time. So let's move on to the next topic. People always ask, well, there's these two engines around, Unity and Unreal Engine, that everybody keeps talking about. So which one should I use? Maybe to ask what's different between the two engines, it's more appropriate first to see what they have in common, because they are actually quite similar in many respects. Both of them are complete game development environments. They run on all major platforms and support many target platforms such as PC, mobiles, consoles. They support state-of-the-art 3D rendering, and both of them are very well suited for creating XR experiences. What they don't have is built-in support for GIS data and coordinated systems, for instance, yet. I will come back to this a bit later on. Let's look at the differences. First, we start with licensing. Unity has a paid subscription model. That means you pay your subscription fee but don't have to pay any royalties. The source code is generally not available. In contrast to that, Unreal Engine has two different licenses. One is the publisher's license, which is royalty-based, and then there's a creator's license, which does not include any royalties and is free but has other restrictions for distribution. For Unreal Engine, source code is available, but it's not open source. But this is really handy if you need to look into the engine source code if something's not working for the way you're expecting it, and you can go and have a look at the source code and also try fixing things and so on. Both companies provide options for custom licensing for big studios, for instance. And as a reminder, licensing details are really important when you are choosing your engine. So this is quite an important topic. It depends how you want to distribute your product, how you want to evolve it, how long you want to work on it, and so on. In terms of technology, Unreal Engine tends to be better suited for high quality and performance applications. It has more advanced render features like ray tracing, sky atmosphere models, and so on. It can easily be customized with C++ code. Unity, however, is only lagging a little behind and is increasingly also providing more high-end features. Unreal Engine has a visual scripting system called Blueprints. This makes it really easy to prototype functionality without coding. You can implement high-level concepts where C++ would be too much. Unity so far has no such feature, and scripting happens usually through C#. The Unreal Editor environment is completely customizable, so you can use Blueprints, Python, C++ to add your own functionality. Unity also allows extension of the editor to some degree, but it's less than you can do with Unreal Engine. Unreal Engine then also tends to be more heavyweight in terms of resource consumption than Unity. So Unreal is really a really big engine, and the editor has requirements on your computer if you want to use it. Unity is a bit more lightweight in this respect. Let's have a look at adoption. Unity is really popular among beginners. It has a lot of indie developers. It roots in 2D and has a mobile focus originally. So as I said already, the 3D engine is constantly evolving with new features. The non-game support is only just now emerging, so it's been mostly used for games so far. It has a really large community. In contrast, Unreal Engine may not be very beginner-friendly. It's often used in larger projects and AAA games. It's really made for high-end 3D rendering. As I said, it's quite resource-hungry, it's big, but mobile support, for instance, is also catching up with Unreal Engine. It has a very strong non-game support by Epic, where they focus on AEC, CAD, simulation, and so on, but it does have a bit smaller community. So, what's our conclusion so far? I would say in terms of development environment, both are really very exciting and user-friendly environments. In technology, I would rank Unreal Engine as the winner, and in terms of community, I would place Unity as a winner, so we have a draw in total, and so it's really by case where you need to choose which engine you want to use. Let's move on to the next topic. How do we get GIS data into game engines? So first of all, we should notice that game engines have some limitations for geospatial and CAD data. Traditionally, game engines work in a local coordinate system and are not able to cope with georeference systems. That means before you can import your data into a game engine, you must transform it, which means typically center your data around the origin. Then game engines typically work with 32-bit floating point precision. That means the extent of your data must be within your limits. Of course, that depends on the base unit that you apply. For instance, in Unreal Engine, it's 1 centimeter. So if you have extents of tens or 100 kilometers, this is going to be a problem. Optimization. Game engines focus on rendering with some additions for physics, for instance, like collisions, and therefore optimize geometry heavily so it can be batch rendered. That means that your original data is typically transformed and turned into unstructured objects. That makes it hard later on to interact with these objects or to retrieve semantic information that was originally present. But the good thing is there's quite a lot of work going on to address these limitations at the moment. So, getting CAD data into game engines, is it really that complicated? I found this figure in a research paper which shows a number of applications that basically circle around the Unity game engine here. Everybody who works with concrete projects knows that there's a lot of tools involved, a lot of different file formats, and you always keep on trying like how can I get my data from one application to the next. What we see here that into Unity in this case, there's the FBX format is something that's rather frequently used. So FBX has really been the classic option so far. FBX is very well supported by both Unity and Unreal Engine. Many 3D modeling and CAD tools often provide FBX exporters. So in theory, this should all work nicely. In practice, however, this looks a little bit different. It's typically quite messy. It's not just for FBX, it's also for other formats. The problems are often a bit deeper. You know, you have incompatible format versions. They're deviating from the standards. You have problems with mesh and material handling. You have problems with handling large models, so your software just ends up in an endless loop and nothing happens anymore. And very often you also don't know where your source data is coming from. You just get from a third party, you get an export from a CAD program, and you don't exactly know which version it came from and so on. So this leads to many problems if you try to deal with these kind of formats. Now there's a different approach that the game engine companies have been working on. That's Unreal Datasmith and Unity with PIXYZ. In this figure you see Datasmith as a diagram. The idea basically is that the game engine has an API or a custom importer and provides a library that the other tools can use to export the data. So basically the game engine tells the other applications in what form it wants the data to have or to get. It's similar in the Unity PIXYZ case. PIXYZ is an external company, so they don't belong to Unity, but they work closely together. So basically what they do here also is to take external data, transform it, and then feed it directly into Unity, so you can be sure that the data arrives in the game engine the way the game engine expects it. Data prep. Data prep is a relatively new term. It's something that you do within the game engine, namely you transform your data so it fits the engine. That means you can typically hook into the engine's import process to filter, to optimize, to replace, to enrich your data. In Unity, you would use custom import scripts, or you use PIXYZ. In Unreal Engine, it's built in, so you can use scripted or visual data prep. Like in this example, you can basically build a data flow graph visually and say what you want to do with the data you import. So how can we get geospatial data into game engines? And here CityEngine comes into play. CityEngine has a lot of connectivity for import, so you can import BIM and CAD models using FBX, for instance. You can get base maps through the get map data mechanism. You can sync from ArcGIS online. You can get sync in layers. And then you can export all that either using the Datasmith exporter and use the Datasmith importer on the Unreal side to import your data, or you can export an FBX which you can use to the Unity editor. So now let's have a look how this works like in Unity. Here we have a typical city in CityEngine. You have generated models. You would just do a selection. You would then go and say, okay, I want to export these models. You select the Autodesk FBX exporter. You tweak some of the settings. What's really important here is that you embed the textures so they will show up in the inside Unity again. And then you basically just drag and drop the FBX file into the Unity Assets tab and then into the scene, and the city will show up inside Unity. Now you have your little city there. You can go and place your camera to a location wherever you want, and that's basically it. From there you can start building your experience. You can add virtual reality extensions, you can add a virtual reality camera, motion controllers, and so on. And then basically just keep adding features, whatever you like for your experience. So in the end, you just press play, and then in this case here, you get the camera. Of course, there's no additional functionality like moving the camera around. But if you look at a few Unity tutorials, you will see that this is really easy to achieve. Now let's look at Unreal Engine. The workflow, as I showed before, is actually rather similar. You just do it with Datasmith export and import this into Unreal Engine using the Datasmith importer. So we will focus on a few different things here. So first you see a high-speed run-through of the Unreal Engine workflow. First, we have in CityEngine, we have some buildings which are being modified, and because it's all procedural, you can easily go and change parameters. And now we just export everything using Datasmith and import this Datasmith into Unreal Engine. This often takes a bit. Yeah, this can take hours if you have really large scenes. And then we have everything. And you can already see, okay, the look is already very, very different from what you have in CityEngine. Now you can go on and start tweaking your scene, tweak the lighting, change the backdrops, for instance, change the fog, the atmosphere, change camera settings. You see the blur in the background. And this is what the final result looks like. So, unfortunately, the process for getting a CityEngine scene into a game engine and having the final result is not fully automatically. It requires quite a bit of tweaking for materials, for assets, for the lighting. So first, let's look at the materials like in this slide here. In CityEngine, you would typically use so-called preview materials, which are a bit lower quality than you would use in a game engine where you use typically high quality, physically based rendering materials these days. So you need to replace the preview materials with the high quality materials. In CityEngine, you can do this by setting up your materials in CGA code like you see here. So basically you will prepare for the UE mapping. You just add a texture in CityEngine. This is what you will see. But then you basically set a material name, you set a shader, so the Unreal Engine in this case will know which material to use. Similarly, we can also use just placeholders if a scene is becoming too complex to be rendered within CityEngine. Like you see here on the left-hand side, you see just colorful dots, which are placeholders to tell the game engine later on, hey, we want to replace that with high-quality assets. This is what you see on the right-hand side. So we get all these vertical plants here. that have replaced the original simple placeholders from CityEngine. So we go from CityEngine CGA code into Unreal Engine with placeholders, replace these with static meshes, which are then used by the Unreal Engine foliage system. We have also created a UI for batch replacement of large amounts of placeholders of assets. So you can have many trees and bushes, or also other props, street furniture, and then select them all and just go and do batch replacement, which speeds up the whole process quite substantially. Here you see a couple of results. So this is a sidewalk greenery after applying asset replacement. So we had just the placeholders within CityEngine and then replaced these with flowers and weeds. In this case, we have seen that nice scene already. So basically for the street lamps that have active lights here, we replaced them with Unreal Engine's scripting system with the so-called blueprints, and you can control them dynamically, for instance, turning on and off the light depending on the time of day. Another interesting thing is that the terrain remains editable using brushes and other landscape tools. So in this case, basically the terrain was originally flat, and we just went in there and used a landscape brush to dig a little pond and fill it up with water. And of course, inside the game engine, you typically have realistic skylighting and cloud rendering, which adds a lot to the realism and the ambience of a city. All right, let's come to a summary and give an outlook as well. Game engines are really great for building real-time 3D experiences. They provide most required features also for AR and VR out of the box. However, they are heavily specialized on graphics performance. So if you want to build an experience with special requirements, you will typically have to code. Unreal Engine and Unity have many similarities, also some differences that we have seen. So depending on the experience you want to build, you probably want to analyze the characteristics of both engines and then decide which one you want to use. Importing CAD data is generally well supported. Importing GIS data currently still has limitations. CityEngine here helps to combine GIS and CAD data and resolve some of these limitations. So, as an outlook, with the growing use of game engines for non-games, AEC, CAD, and so on, the engine companies are increasingly interested in GIS data as well. So we can expect enhancements to the existing engines to better handle GIS data soon. In addition, we will see integration of CAD and GIS-enabling software directly into the engine. For example, CityEngine integration, plugins to generate procedural geometry directly within the engine. And another example is the ArcGIS integration, which are plugins to access GIS content from within the engine. For the first one, I show an example here. The plugin is called Vitruvio for Unreal Engine. It's basically a CityEngine plugin for Unreal Engine and contains the geometric kernel of CityEngine within this plugin, and you can directly generate buildings within the engine, like you see in this example. So you have in your details panel of the inspector in Unreal Engine, you can go and change your attributes and control the generation of the buildings, and the buildings will continuously be regenerated. For the ArcGIS integration, I will show an excerpt from the plenary of Dev Summit 2020. of the ongoing integration of ArcGIS.
You can tell amazing stories using GIS, but if you combine GIS data with the power of a game engine, you can take these stories to the next level. This is our second product, and I'm going to show you a simulation of the fires that took place in Australia using Unreal Engine. This animation shows all the locations of the fires during the month of January. The fire locations are coming from a feature service in ArcGIS Online. This may look like a typical GIS application that we could build today, but to understand the real impact on the fires, we can use the visual and storytelling capabilities of Unreal Engine. Let's start by changing the base map. The combination of using a imaginary base map and clouds generated by the game engine give us a more realistic view. You can use Unreal Engine to attach particle systems to our GIS data to better represent them. In this case, adding a smoke coming from the exact location set in our feature service in ArcGIS Online. Now, you can have a better idea of how impactful the fires were on a global scale. The smoke was visible from the space station and even covered a grand part of New Zealand. Moving closer to the Australian coast, we were able to see the devastating consequences of the fires, with the smoke blocking the sun for a large part of the country. Using the API, you can move the camera for the smooth camera animations, but at any time, you can interact with the scene. Finally, for a very immersive visualization of our data, we can move to the ground level and take a look to a single feature point. The true power of Unreal Engine comes from the ability to render high-quality walls. GIS is no longer bound to static maps. GIS can live in real time. And yes, now the room is on fire. Back to Iwan.
So yes, this is really, really exciting stuff coming up, and I suggest that you stay tuned and check out our videos, especially with the ArcGIS integration for both Unity and Unreal Engine, which the beta program will be available this summer with final version expected in towards the end of the year. That is it for this presentation. I thank you for your attention, and goodbye.